right. Anything I can do for y'all? I guess Liv isn't here yet, but. Do we have an assignment out? Probably not, I think, right? Okay, good. Then I won't feel bad about putting this on the board. I might feel a little bad about it. Let me take a look one more. Let me look at this one again. It's like, I don't know. I don't want this to be too big, and I know you agree. Oh yeah. Yeah, we'll just do 86. All right. Probably second to last homework. Probably give you one more that'll be due finals week. And then I'll have big old office hours during our final. I can come sit in here if you'd like. If that would be something you would prefer, I can come sit in here and you can come work, or just go sit in my office, which is kind of like preferable, but I would totally be here for you. I have to look at the note I wrote on this one. So I think those 4 problems, but I'm gonna look, I have a note on 19.2b. Yeah, that's a good one. I don't know what the note's about. Let me look at 19.6 too. Oh yeah, that should be good. Not sure what my comments are about. Just those 4. When do you think? Next Wednesday? Sound good? Nice. All right, that orange isn't as bad as you would think it would be. But we'll go to blue anyway. You're probably sick of reading about the intermediate value theorem. I'm imagining, right? Like, can anybody tell me what the intermediate value theorem says? Can anybody not read it to me? Because I can read it. Does anybody just happen to remember it?
It says something along the lines of, if a function is continuous on some interval,
like this,
and there are points A and B on that interval such that A is not equal to B, and either f of A is greater than f of B or f of B is greater than A,
yeah,
then there is some value y, or I guess f of y, that lies between f of A and f of B. So there'd be like a corresponding input that would go to that output.
Yeah, that's pretty damn good.
I don't know, like the jargon.
I don't know, that was pretty good. I think everybody's probably happy you came up with that. So yeah, it basically says this, that if I have a continuous function on an interval, and it's got some value at the start and some value at the end, and we could assume this one's bigger or this one's bigger. So there's 2 cases for this, and that's what Christian was kind of like talking about. Either it starts smaller than it ends, or vice versa. We're going to assume that there's somewhat of a difference in there. Then you pick a y value between these 2 outputs, and it is achieved somewhere in between. So if I've got f of A less than f of B, then for all y such that y is between those 2 values, there exists this x tilde in the interval such that f of x tilde equals y. every value between these two is achieved. Every intermediate value is achieved by a continuous function. So we could go through the proof of that, but you could also read it. And I'm kind of hoping that if you hadn't read it, you read it again. The proof idea is pretty chill for the most part. What we do is, just to give you an outline so that when you go read it, it makes a little more sense. So we've got our function. We're going to assume f of a is less than f of b. And let's see, so then there's a, and then again there's b. And we're going to pick a y value between these two. And then we're going to create this set S, which is the set of all x such that the function is less than that y value. So this is the set y at S that they create. And so what that looks like is if you mark off this y value here and look for where the function crosses that line. S is all the inputs that keep you less than that value. So this is actually S. And so the idea of the proof is this then. We've got this set here. We know this set is non-empty because f of a is automatically less than the y value. So a is automatically in there. Got that. And we know it's bounded because S lives between a and b. So it's just by definition bounded. So it has a supremum by the completeness property. Got a bounded, non-empty set, it has a sup. And so we say, all right, well, let's let x tilde equal the supremum of the set S. By definition of sup, we know that there's a sequence of points in S that converges there. And all those values are going to have f, so there exists this sequence, x sub n in S. X sub n converges to x tilde. So since f is continuous, we know that if I plug this into f and this into f, I get that same convergence. So we know that f of x sub n converges to f of x tilde by continuity. But we also know that each one of these x sub n's is in this set S. So this thing is actually less than y no matter what. Since these x sub n's are in here, this value is less than y. And so when you take the limit here, you get that f of x tilde must be less than or equal to y, because even though you're less than, as you take the limit, you might actually hit it. So we get this inequality, and then we do a quick argument to show that there's stuff here on this side. In other words, that x tilde is not equal to b, which is a pretty straightforward argument. And then just take a sequence on this side that converges. So then we have a sequence that converges from the outside. So we've got this sequence t sub n that converges to that same sup, but from the right side. And what you have to think is, what's going on with f here? So, well, f of that tn is actually bigger than or equal to y. So that, when I take the limit here, this converges to, that just converges to f of x tilde, and I get it greater than or equal to y. So look, you get two inequalities here. You get, where the hell is my first one? I get the first inequality that says this, f of x tilde is less than or equal, and then I get the second one that says it's greater than or equal, and so the only thing it can be is equal. That's the proof. You could read through it. That's kind of it in a nutshell. But what I wanted to talk about are some of the consequences of the intermediate value theorem, because there's some cool stuff. Some of you are going to go be teachers, and maybe someday you'll be talking about this, and you have some cool examples to pull out. Consequences of the intermediate value theorem. So I think one of my favorite applications of this is kind of a geographic like a nature fact about Earth that you can deduce from the intermediate value theorem if you look at it just the right way. So let's take a look at Earth. Pretending Earth's a perfect globe. And I'm going to think about being on the equator. And I'm going to measure the temperature. So here we have T at, let's call it theta degrees. So think about how you might navigate on the equator. You might have theta equals 0 there and then sweep 10 degrees that way. And so then theta equals 10 here. Just think about the degree measure along the equator. Does that make sense? And you've got 360 of them. So I'm going to say T at location theta on the equator is the temperature there. In, let's just say, degrees Celsius at equator location. Theta. Cool. What is T of theta plus 180 degrees? What is that giving me? Like just story, part of this story. So here I've got the temperature right here. Maybe that's us. That's temperature at theta. What's this represent? Temperature where?
The other side of the world.
Complete other side of the equator. Yes. So this equals the temp on the antipodal, which is a great word, antipodal location. Straight across. So let's say now we're going to create this new function. And I guess I have to have you buy in to this observation first, that as we travel along the equator, the temperature changes continuously. So can we believe that? I've only had one person who wouldn't believe this. He didn't have a good argument for it. But that as I move through the world, the temperature changes continuously. The temperature isn't suddenly 0. You don't get temperature drops like this. Does that make sense? Like the temperature just can't drop. It can drop like this. It can drop precipitously, but not just instantly change. Does that make sense? I think to me that makes a lot of sense. That seems like a real fact. This guy was like, he was just a troublemaker. He was a super smart guy. Troublemaker though. So let's take a look at this difference function. So the difference of the temperatures on the two sides of the Earth. So first thing I'm going to have here is T of 180 plus theta, and then minus T at theta. So this is kind of the temperature difference between here and then that other side point on the other point of the Earth. How much is the temperature difference? So if we're assuming that T is continuous, and I think you believe me, and I think I believe that you believe me, then this is also continuous because it's just the combination of continuous functions. So that difference should change continuously. Awesome, cool. So let's take a look at D of 0 degrees. So at 0 degrees, I've got T of 180 minus T of 0. Now, either these two temperatures are the same or they're different. If they're the same, then I've instantly got two places on the equator across from each other that have the same temperature. And that's kind of what I'm trying to argue is that's always going to be the case. When you're on the Earth, there is always a location directly on the other side. Well, you have to keep moving, but there's always two locations on Earth opposite each other that have the same temperature. That seems pretty weird to me, but we can prove it with this. So let's say that these two temperatures aren't the same. So let's assume this is positive because the temperature on the other side of the Earth is bigger than the temperature at 0 degrees. Let's just say that. So this is the hot spot over here. And this is the cooler spot. So now what happens when I look at D of 180? Well, D of 180 gets me T of 360, which is actually T of 0. And then this becomes minus T of 180. Do you see how I made that slip, that that's 360, but it takes me back to the start? What can I say about the sign of this? It's negative, because it's the reverse of this. So if this is positive, this must be negative. So now let's think about this. I've got a continuous function, d, and between 0 and 180 degrees, so here's your theta degrees. It starts off positive here. We don't know what it is, but it's just positive. It's this value right here. And then it ends up negative over here. What does the intermediate value theorem tell me? Tells me that since this is continuous, that every single value here is achieved somewhere. So in particular, somewhere it must spit out a 0. I don't know where, but somewhere. So by the intermediate value theorem, there exists some theta tilde, we'll just call it that, such that d of theta tilde equals 0, i.e. t of 180 plus theta tilde equals t of theta tilde. There's always two places on the earth, no matter what big circle. So this is kind of crazy because this works with not just the equator. You take any big circle on earth, there are always two places exactly opposite each other of the same temperature. And to me, that just seems wild. I don't know, it doesn't seem real, but it must be true. It must be true if temperature changes continuously. So, I don't know, your mileage on how amazing that might be seems a little different maybe than mine, but I find it pretty cool. Maybe you'd like a more mathy example, and I got that for you as well. So let's take another grok here at something, get a fun math fact out. Fun IVT fact 2. If t, I don't know why I'm using t, let's just use f. If f is a function from 0 to 1 into 0 to 1, so closed intervals 0 to 1, 0 to 1, is continuous, then there exists at least one fixed point. Do you know what I mean by fixed point? I.e. some, at least one, x tilde, we'll just go for it again with the tilde, such that that input goes back to itself. Let's kind of think about this. So here's 0 to 1, here's 0 to 1. And what I'm saying is that there's always, if you have a continuous function from 0 to 1, there's no way to create it without crossing that diagonal. Because when I cross that diagonal, I've got a fixed point. So there's always going to be at least one fixed point in there, but we can prove it really nicely with the IVT. So let's do that. We're going to create a new function like we did over there. That's a lot of the trick to these IVT things here. That's the same color. Okay, cool. Let me try this stuff. So let g of x equal f of x minus x. And then let's look at g's values at 0 and then at 1. So g of 0 is equal to f of 0 minus 0. Yep. Okay, cool. And because this function maps from 0, 1 into 0, 1, f of 0 has to be bigger than or equal to 0. Simply because that's its output space, right? Saying this means that f of x always falls into this range here. So it's bigger than 0, bigger than or equal to it. And then g of 1 is equal to f of 1 minus 1. But I know that f of 1 is less than or equal to 1 because it's also in this interval. But let's write that out. Since f of 1 is less than or equal to 1, this is less than or equal to 1 minus 1 equals 0. Write up what I just showed there. It's this weird little construction. And we've got the answer maybe at one of our endpoints. And if we don't have it at our endpoints, the IVT gives it in the middle. So g of 0 is greater than or equal to 0. G of 1 is less than or equal to 0. And g is continuous because g is just a combination of two continuous functions. We assumed f was continuous. So g is continuous. So now check this out. Either we can get our fixed point at the left endpoint. So if g of 0 equals 0, we're done. If g of 1 equals 0, we're done. Guess we're not done there, are we? So we're going to assume that, so we're going to assume that g of 0 is positive. Otherwise, we already got our fixed point right there. So now let's look at the picture. G of 0 is positive. G of 1 is either at 0 or it's below 0. So g of 1 is somewhere in that range right there. If g of 1 equals 0, then 1 is our fixed point. So let's put that up here. If g of 1 equals 0, then f of 1 equals 1, and we're done. So let's assume that g of 1 is not 0. That means it must be strictly less than 0. So g of 1 is going to be down here. Do we see how the intermediate value theorem now gives us? Got to cross somewhere in between here, and that's going to be our x tilde. So by IVT, there exists some x tilde, and we can actually say it's in the inside of that interval because we've ruled it all out, such that g of x tilde equals 0, i.e. f of x tilde equals x tilde. So two similar applications, they both involve that kind of sneaky creating that difference function there. And I'm going to let you contemplate this quickly while I go pee really fast. I'll be right back. Excuse me. Thanks for waiting. I feel like my bladder's gotten really tiny over like the last 2 weeks. I don't know what's going on. I know that's too much information, but it's the truth. I'm finding myself in these like moments where it's like, oh my God, I gotta get out of here pronto. So I have a quick question for you. Question. Do continuous functions preserve Cauchy sequences? Wow, this pen is losing it. Can you all read that okay? Do continuous functions preserve Cauchy sequences? What's a Cauchy sequence? So,
Closed and bounded.
oh, that would be a compact set,
That's right.
closed and bounded. So X of n is Cauchy. I thought this would be a good thing to review. Seems like I was right. Is Cauchy if what? Impromptu quiz. No karma.
Is it monotonic?
It could be, but that's not the characteristic. Oh, I think it's good we talk about this again. I think this will be on the last quiz of the year too. If for every epsilon greater than 0, what does it mean? So let's slow down a little bit. What does it mean to say converges? What does it mean to say a sequence converges? I'll be even kinder. 2x. You guys just let me know. Get some tea. Got a nice empty bladder. I can drink tea for an hour. Hear that tea sound? What's your time running out?
Is the convergent one like converges to x if for all epsilon greater than 0 there exists another x, like x of 0, such that x minus x of 0 is less than epsilon?
There does exist something, but it's not the x sub 0. So I got the x sub 0 is going to be my limit
Okay.
here.
Oh, it's like L. There exists some L such that.
Or some capital N,
Yeah.
big N.
Oh, and
Oh,
then
that's
every-
right.
Yeah, this is good. Okay, cool.
Such that like little n, when little n is larger than big N, x of n, or the absolute value of x of n minus x naught is less than epsilon.
Yeah,
Okay.
all right, we got it. A little painful, but we got it. When I was in grad school, I took this class in differential geometry with this. There was an independent study with Dr. Jaak Wilms at CSU, and we had our final exam at a bar, and he just bought pitchers for us, and so we just were drinking pitchers of beer, and then like about an hour in, he says, "Okay, so we better have a final." And it's like, and I was already like, and no one could even define the title of the class, and we all got A's. Grad school. It was sad. I think he was embarrassed. I think he realized that it was a little bit his fault that we didn't know. Mostly our fault, but you know, he trusted us to learn stuff. We did not. We got this though, right? That's convergence. So how does Cauchy differ?
Cauchy is, there exists some capital N such that, or wait a second.
It's already so much better. We're
Okay.
already moving forward.
Okay, such that, little m and little m greater than big N implies that the absolute value of x sub m minus x sub n is less than epsilon.
Hell yes.
So that's like, it's like getting like closer towards the end, like the behavior kind of.
100%. So convergence, you have to have where you're converging to. When I talk about something converging, I need to know where it converges to. And this is saying that I can get as close to that as I want by moving out far enough. Cauchy is about closeness and clustering. Cauchy doesn't need a limit. We can say a sequence is Cauchy, and that just means that things bunch up as we move out.
So it's Cauchy though, doesn't that imply boundedness?
It does. It does. And why is that? So hold on. Okay, let's we're getting Cauchy implies boundedness, but it also implies what in the reals? Is every convergent sequence Cauchy? I think we need to let's go back and talk about some of this stuff. Here's some questions I have. Start there. How about that? Give me an example then of a convergent sequence that is not Cauchy.
A sequence that is just the number 1.
Like this? Cool. Does that converge? Where's it converge to?
1.
Cool. What is x sub m minus x sub n for any m and n?
1 minus 1.
It's less than the third.
So it would be Cauchy, wouldn't it? Eventually, everything's always no distance apart. So it would be Cauchy.
Like, wouldn't convergent sequences have to be Cauchy because of the fact that, and I don't know the name of the theorem, but the one that says that, like, it's not just Bolzano-Weierstrass where it's like every bounded sequence contains a convergent subsequence, but the one that says, like, for a sequence to converge, like the subsequences must converge to whatever that point is, right? Or am I mixing?
Yes. No, you're not. Yeah. No, that's completely right.
And so, like, doesn't that kind of imply that, like, the end behavior is all gonna, like, settle into, like, the same place for any given subsequence?
Yeah. Absolutely. Let's prove it. Let's go through the proof of this again. So let's let x sub n be convergent to some point. I'm going to go with the tilde because that's what's been in style the last 2 weeks in my world. I'm going to let it go converge to that. Need to show x sub n is Cauchy. So I'm going to pick my epsilon, start there. The only thing I can control is this stuff, because this is all I know. How could I possibly move from this or this to this? How can I move from manipulating things, because I can control these, this is what I want to control. Suggestions.
It's the triangle inequality, isn't it?
Slip in that X naught. Triangle inequality. direction of those? Awesome. So if I want to make this less than epsilon, what do I have to do to these guys?
Make them less than epsilon.
Over 2. So I'm going to choose big N so that when M or N is bigger than that N, we are half that epsilon close to our limit point. And I guess I said this was that tilde. It's less than epsilon over 2. So just use the convergence to X naught to get this guy less than epsilon over 2, this guy less than epsilon over 2. And then that same N now works to get these guys less than that. Is every Cauchy sequence convergent?
There's something about it doesn't work unless you're in the reals, like.
That's right. But in the reals, it's definitely true.
Yeah.
Yes, and this was a trickier thing. This was a very fancy proof. But remember, in the reals, in any dimension, Cauchy is identical to convergent. The only difference is when you have Cauchy, you don't need to know the limit. But you could find a limit if you wanted to. So now we kind of know something, we recall something about Cauchy sequences. Do we think convergence, that continuous functions preserve said sequences? Give me an example of a Cauchy sequence that converges to 0. Could I please have a Cauchy sequence that converges to 0?
1 over x then.
1 over what?
Just like x.
Or n, yeah.
Yeah.
So this converges to 0, therefore it's Cauchy. So there's a sequence, a Cauchy sequence, that converges to 0. Can you find me a function f so that f of x sub n is not Cauchy? And I want f to be continuous. At least where the sequence value lives. Can you think of anything you could do to that sequence to make it not convergent with the continuous transformation? Thinking about all sorts of weird functions. Here's f of x, here's the points converging, and it looks like the sequence points up here. No, that all converges.
Couldn't you just do like anything that oscillates to get like a function that's continuous that's not Cauchy?
A function that's continuous.
Is that what you're asking for?
Kind of. I'm looking for a function that would screw up, that when you ran these points through it, it would make them not Cauchy anymore, not a convergent sequence anymore. Is there anything I could do f-wise, f of x equals what, to take this sequence and make it not converge? What if I made it a little bit better? I've got f from 0, 1, not including 0 and 1, into the reals. Oh, here, make your life even better.
Saying like change 1 over n? So
Yeah, use it, through some transformation. What?
Did, like, changed it into n squared over n, that would go to infinity, no?
Yeah, how could we do that with a formula? You're on the right track for sure. What if I just let f of x be 1 over x? Then what is f of x of n? It's n. So in other words, if I have the function that is continuous on 0 to 1, so take f of x is 1 over x, That's continuous on 0 to 1, not at 0, but that's okay. This sequence lives inside that domain because it never hits 0, but f of x sub n is n. And that is not convergent at all. That thing blows up. So as you're moving in here, when you got 1 over n here, you've got n as your output over here. As you move this in, these guys shoot up. So the answer would be no. They are not preserved. But there's a different flavor of continuity that's a little stronger. And that's what I kind of want to talk about. Mostly that's what today is about. Maybe a little bit Monday. However, and we'll put the punchline here and then we'll show it. However, a uniformly continuous function does preserve Cauchy sequences. That's one of the nice things of this new, stronger flavor of continuity we're going to talk about. So let me get the definition up here, and then maybe you can tell me what's different. We say f is uniformly continuous on a set. We'll call it D reals. If for every epsilon greater than 0, there exists a delta greater than 0 such that when x and y are in this domain and x minus y are delta units close, less than delta units apart, we have f of x minus f of y less than epsilon. How does this differ from continuity?
Refers to continuity over a set of, a set of points instead of just at a point.
Yeah, definitely. So it's about multiple points. So let's put up the definition of regular continuity and just contrast. So that's definitely right, Christian. Regular continuity. So we say f is continuous at a point. So this stuff's just about at a point. If for all epsilon greater than 0, there exists a delta. So everything starts out the same, such that when x minus x naught is less than delta, that implies f of x minus f of x naught is less than epsilon. So notice over here, I've got this one delta, and it works for every single x and y inside D, inside the set. So like Christian said, this is about a set. This is about at a point. And that delta over there, you get one delta that works for the whole set, no matter what epsilon is. So over here, you set epsilon. You can pick one delta, and it works all over the entire set. That single delta works for no matter where you're at. Over here, this delta, for each epsilon, delta depends on the point you're at as well as epsilon. Over here, delta only depends on epsilon. Actually, let's see, let me bring up the app here so you can kind of see what I'm talking about. And this would be nice just to have a little change of scenery besides me.
Does that mean there's like with uniform continuity, there's some like constant in like the rate of change, or like there's some like kind of window
Yeah.
it has to be?
Yeah, absolutely. Yeah, the derivative is bounded in a way, and I think that's what you're picturing there.
Yeah.
Yeah, absolutely. take a look at Desmos. Ooh. Sure. Plug in that means. Seriously? No, I'm talking about math, man. Not like flights. Calculus. Give me the app. Okay, I have to tell it maybe GeoGebra. There we go. Perfect. This is exactly. Do they let me pick the function? Do you see where I can choose the function? I don't really see it. Well, I think this will work. I kind of wanted to be able to enter my own function. So, can we move this L? This one kind of sucks. Can't really do anything with it. I want one that's got more control. There we go. There we go. Now we're talking. All right. So let's get a better function in here. Let's do one over that. Bless you. Fantastic. Okay, so here we've got f of x is 1 over x squared, and that's clearly not defined at 0. Let me pick a particular epsilon. So hopefully, so the epsilon is that red bar. That's kind of like my epsilon tube. They don't show it extended out. And then the delta controls all the inputs that land inside there. So watch what happens here. I've got a particular epsilon, and so epsilon is that thickness right there. As I move the point I'm at, notice how the output window changes. So that epsilon works here, works here. Now it no longer works. Do you see how the spill from the input comes outside that band? So what we're looking for is uniform continuity means I set this width right here, and no matter where I'm at down here, as long as the delta remains constant, I can still land inside there. But here, things are not good. Look at how huge it gets way up there. And then over here, everything's just completely fine. So uniform continuity would mean something like over here. Turns out this function is actually really not uniformly continuous on this side, because you get that blow up, but it's absolutely uniformly continuous to the right of 1. Let me show you what I mean. All I have to do is set my epsilon to be big enough. So look, right now, all my stuff hits inside that epsilon window, and as I move this way, I stay inside that window, so it's independent of the x, it's independent of where I'm looking, and it's also independent, well, I do have one delta that works. You still just get one delta response. But the key thing is, it doesn't matter where I'm at, as opposed to over here. So that's the idea of uniform continuity. Let's get into the math of it. So I think the best way is to see a couple examples to understand this. Actually, fun one for you. What is not uniformly continuous? This is one you can do. Give me the negation of that definition, please. So node. If we're getting nothing else in this class, we're getting lots of practice with contrapositives, negations. Node. F is not UC on a set D if what? We got some? Maybe? How's it start?
There exists an epsilon.
That's a good one. Yeah. Right, we got that. Flip that.
And you also flip the other quantifier, should be for all delta greater than 0.
Exactly. And when you do this flip, I always like to put a such that it just flows a little better. There exists some epsilon. And let's say epsilon naught, because we know it's like a thing we're going to fix, such that when for all delta greater than 0. Now what?
If x, y are like elements of D,
Yeah.
The absolute value of f of x minus f of y less than epsilon does not imply x, or the absolute value of x minus y being less than.
I don't know about that negation there. I like that. I think we were feeling pretty good up till then. That was feeling good. What's the negation of that?
P and not Q.
P and not Q. That's how we got to negate that. I think you were doing like the converse or something. Yeah. So P is the condition that these guys are less than delta. So I still got that, such that difference between x and y is less than delta. And f of x minus f of y is not less than that epsilon. In fact, it's greater than or equal to that epsilon. So think about what this means. It means I can find, if it's not uniformly continuous, I can find some x's and y's that are getting closer and closer together, because this is for any delta. So I can get these as close as I want. Erstwhile, the function values are kind of fixed apart. They're kept this far apart, no matter how close the inputs get. So check this out. Outputs remain, there's a gap of epsilon naught, at least in the outputs, even though the inputs are getting closer and closer together. So let me give you an example. Let's go to the one that I had up on the screen there. So f of x is 1 over x squared is not UC on the interval 0 to 1. Actually, then let's actually write one more characterization of not UC, because I think this will help you when you need to do it, and you will need to do it. So, best characterization of not UC on a set D. And what that is that there exists some epsilon naught such that there exists an epsilon naught and a sequence of points x sub n and y sub n x sub n and y sub n in D such that x sub n minus y sub n are becoming infinitely close together. So this is the x minus y less than delta, but f of x sub n minus f of y sub n is stuck apart. So it's all about finding two sequences that are shrinking together. They're getting closer and closer together, but the function values are staying apart for the outputs. So this guy is a perfect example of that. To show this is not UC, I'm going to let x sub n equal 1 over n. I'm going to let y sub n equal 1 over n plus 1. So now check it out. So x sub n minus y sub n, if I look at that absolute value, that's going to be that's just this, and that shrinks to 0. So these two can get as close as we want. So x sub n minus y sub n is converging to 0. But f of x sub n is what? It's n squared. And f of y sub n is n plus 1 quantity squared. So the difference between these two, so f of x sub n minus f of y sub n, is the difference in these guys, n squared minus n plus 1 squared, equals, what's left in here? These n squareds are going to cancel. You're left with 2n plus 1 inside there. When you FOIL this out, you get n squared plus 2n plus 1. Taking the absolute values, you get this. And so this right here is greater than or equal to 1, no matter what. What this is saying, draw a picture so you can have something nice to understand this from. That if I've got 1 over n here, and 1 over n plus 1 right here, that this output is n squared, and this output is n plus 1 squared, and these two are always 2n plus 1 apart. So even though the inputs are shrinking to become the same input, essentially, the outputs are growing further and further apart as n goes up. So as n goes to infinity, the outputs diverge drastically. So this is how I would argue that f is not uniformly continuous on 0 to 1. However, turns out it is UC on the rest of the interval. So, but f is UC do we show this? Well, we're going to always pick our epsilon to start with. Right, epsilon is greater than 0. We do a little scratch, because we like scratch work. And I'm going to look at what f of x minus f of y looks like. So let's plug in the values. So that's 1 over x squared minus 1 over y squared. And then combine those together. Get a common fraction. And then do something that you kind of just need to know how to do. And I'm going to do it and then explain why I did what I did. So this is a difference of two squares. That's y minus x times y plus x. So I'm going to factor out the x minus y part. Tell me, just make sure you see how I got to where I went there. It's a little bit of algebra. I did the difference of two squares factorization, and then kind of flipped the order on these two because there's absolute values. Does that make sense? Okay. So now, if I can get a bound on this thing, I'm going to be pretty much set up for uniform continuity. We'll see why in just a second. But if I can get this thing to not depend on my x and y values and just get some number here, then I'm home free to getting my delta for an arbitrary epsilon. So what we got to do is think about, does this thing have a max? Is there a max of this on 1 to infinity cross 1 to infinity? And so in other words, the x and y's come from there. So x comes from 1 to infinity, y goes to 1 to infinity. And to see that, you got to do a little bit of work, some more scratch. I'm going to do the scratch right here. Oop, that's times. Break it apart into two fractions. X squared plus y squared. And then cancel. This is 1 over x squared y plus 1 over, that's times, 1 over xy squared. So broke this apart like this, doing some cancellation down here. What about these quantities right here? If the x and y values, so I want you to maybe tell me something about this. If I know this about the x's and the y's, what's the most that could be? Are you holding your finger up?
I think it's 2.
Yeah, okay, you were holding up 2 fingers. Yeah, why? Yeah, you're right. How'd you get that, Cormac?
The variables are in the denominator, so you have to pick like the biggest fraction it could be, and that's when it's 1, and 1 plus 1 is 2.
Yeah, beautiful. The biggest these are going to get is when x is 1 and y is 1, and then when they're bigger than 1, these fractions just get smaller. So the biggest this could be, max equals 1 plus 1. I guess that's just 2, isn't it? Yeah, is it back? Yep, 2. So in other words, we know from scratch that, let's write this out again, f of x minus f of y is less than or equal to 2 times x minus y from that fancy scratch work over there. This is actually a little bit stronger than uniform continuity. This is what's called a Lipschitz function, but for us, this gets us everything we need. So we are home. We are done because, let me explain why. Because now, to get f of x minus f of y less than epsilon, I can control how close x and y just need to be and get that. So we need 2 times x minus y to be less than epsilon, i.e. x minus y less than epsilon halves, and this is my delta. So when delta is epsilon over 2, I have x minus y less than epsilon over 2. That gets me this, that gets me this, that gets me this, and that literally gives me uniform continuity. So let's write this, let's write the formal conclusion up here. And here's a little tip, just tip. Notice how we got f of x minus f of y less than or equal to some constant times x minus y. This is a goal when you're trying to show uniform continuity. When trying to show UC, go for this. Because then once you have it, you can get this whole thing less than anything you want by controlling the size of x minus y. So I guess, let's see. Yeah, let's just finish it up over here. So, given epsilon greater than 0, set delta equal to epsilon over 2, then x minus y less than delta implies f of x minus f of y less than epsilon for all x and y in the domain implies f is UC. Get up a couple nice results that I think are going to help you knock out some things. I'm not going to prove these. I'm just going to pop these up. You can read the proofs in the book, and definitely should read that section if you haven't. Theorem. If f is continuous on a compact set K, then f is uniformly continuous on that set. So if you have continuity and a compact set, you're uniformly continuous on that set. Here's another theorem. If we have a function f from A to B, so not a compact set. So if I know that I know f lives on some open set, but it's not compact because it's not closed, although it is bounded, then f is uniformly continuous on that open interval if and only if f can be extended to a continuous function. On the closed interval. So if you can add a few points that fill in the ends here and keep that function continuous, then it is uniformly continuous. You've kind of put here continuous as well, sorry. F has to be continuous on that set. So for example, this is an example we talked about yesterday. And notice this is an if and only if, so it's very powerful. Is f of x equals sine of 1 over x uniformly continuous on 0 to infinity? How about we say 0 to 1? So it's nice. It is if I can extend it to a continuous function on 0 to 1, but remember what sine of 1 over x looked like? It looked like this. And what we saw was that you could achieve any limit between -1 and 1 just by following the right parts of this function over. You just follow the stuff that's at your level and it cruises in this way. So the possible limits of sine of 1 over x as x goes to 0 are infinite. So there's no one right value that you can put here to extend this thing. So i.e., let me write that out, i.e. no one right value to define at x equals 0 to make this continuous. So it's not uniformly continuous. Whereas, just one last one. If I took whereas g of x equals sine of x over x can be extended to x equals 0 because I know that the limit as x goes to 0 of sine of x over x is 1. You can prove that with L'Hopital's theorem. So what you get when you've got sine of x over x, and I think we also looked at that one, it essentially just kind of, it does oscillate, but as you approach 1, as you approach 0, it actually achieves a limit there. So you could take this function, g of x, you could extend it, and you could say, I'm going to equal 1 when x equals 0, and then sine of x over x when x is greater than 0. And this is a continuous extension.
When you say extending, does that just mean like splitting it up into like a piecewise form?
Yeah, so when I say extending, I mean defining it, just giving it definitions of values on the left and right ends of this so that it's continuous.
Okay.
And you're not just jumping. All right, thanks everybody. I think that's enough. Do you guys want to do something different for class in the last 2 weeks?